Welcome to our fourth lecture in our series about harnessing artificial intelligence. Today we're going to be talking about rule-based artificial intelligence. I'd like to make a few remarks about this before we begin. The earliest mathematical models for computers were developed in the 1930s. So people have been thinking about computers as something we could actually express precisely for quite a long time. Many of you have heard the term Turing machine, named after Alan Turing. His mathematical description of computing was the most famous. All of the original conceptions of computing used the idea of an algorithm that controlled the machine. And the algorithm consisted of a series of rules that the machine had to follow. Today, much of what we call programming is inherited from these past conceptions. Programmers use programming languages today, which are synthetic languages, meaning we've invented them for the purpose of programming. They use these programming languages to express the rules of the algorithms into a form that a compiler can translate into machine code. The earliest artificial intelligence programs sought to automate human thought processes of problem solving, because a lot of people associated human intelligence with problem solving. And these applications, these problem solving applications, were seen as applications of logic and some adding in numerical calculations. So we mixed up, logical things like if, then, else, and then calculations like adding numbers or multiplying numbers. Put all those together and they make up algorithms. A number of computer languages were invented fairly early on to help those who were trying to program artificial intelligence algorithms. Some of you have heard the word Lisp, L-I-S-P, which is the name of a language that was very famous. I think it's still around. Another one is Prolog. It's another famous language used for doing the logic calculations involved in artificial intelligence. Board games like chess and checkers were among the first targets of artificial intelligence programming, because it was commonly said that if you get a computer to play chess, it would have to be intelligent, because after all, human intelligence is needed to win at chess. Well, the first checkers machine was created in 1952 by a man named Arthur Samuels at IBM. And it was a competent machine, but it inspired others to go for more complicated games, and chess was one of the first targets. There's been people working on chess programs for almost continuously since that time. And as some of you may know, in 1997, the IBM Blue computer, which is a chess-playing computer, beat the world grandmaster Garry Kasparov at chess. So it took many years to make chess programs get that good, but they actually achieved it. In recent times, we've heard of some other programs like the Go programs, which have recently come into use, which also play these board games. The most ambitious kind of systems that were tackled in the earliest days of artificial intelligence was the expert system. The expert system is a software system that would contain all the rules that an expert uses to solve problems, and could therefore reproduce the expertise of the expert without having to have the expert actually be physically there. Well, today for our speaker we have Dr. Vinnie Monaco from computer science, who's going to discuss all these topics and give you loads of examples about them, and give you a glimpse of some of the AI problems that these type of systems that are based on rules are good for, and some things they aren't so good for. Vinnie joined our faculty about 1 year ago. He received his bachelor and PhD degrees from Pace University in New York. He worked for the Army at the Aberdeen Proving Ground for 2 years before coming to NPS. His Army research focused on brain-inspired computer architectures to solve traditional problems that traditional computers weren't doing well. He continues this line of interest with his research at NPS, which is, he calls it neuromorphic computing. Neuro meaning something to do with the nervous systems, and morphic meaning following the structure of the nervous system to inspire you for the algorithms. So I present Vinnie. Please welcome him, and go ahead.
Thank you for the introduction, Peter. So in the last lecture, Professor Kroll talked a lot about rules, and in today's lecture I'm going to talk about some of the early attempts and the most primitive forms of artificial intelligence that use rules to try to accomplish this. So we'll be looking at a rule-based approach to artificial intelligence. Start by just going over a quick background of what do I mean by rules and inference, then looking at some of the early attempts at implementing these systems. I'll go into some detail on some of the expert systems that Peter mentioned, and finally draw conclusions. So when I talk about a rule, what I'm talking about is some relationship among symbols. So a rule just establishes a relationship among symbols. This could be an implication. So we could say if some condition holds true, then something else becomes true. So if it's a federal holiday, then we have no classes. This could be a fact, just saying all objects of some type have some properties. So all baseballs are round. Or this could be saying we need some prerequisite in order for something else to happen. In order to request leave, we need to submit a form. So these are just some examples. There are a much wider variety of how you might establish a rule, but they're essentially just statements that establish a relationship among symbols. Now, with these rules, we can perform inference, which means if we have a couple rules or a fact, if we have a statement that says if something is round, then it can roll away, and if we know that a baseball is round, then we can conclude that a baseball can roll away. Now, in rule-based AI systems, there are primarily two ways we can get this information, reach this conclusion. The first is through a process called backward chaining. So in backward chaining, we start with our goal and we work backwards. So we start by asking the question, can a baseball roll backwards? And can a baseball roll away? And we work backwards. We reference our rules and facts in what's called a knowledge base to try to answer that question, yes or no. In this case, we would say yes, it can. So that's backward chaining. The other approach is forward chaining. So we can work from the other direction. We can start with our knowledge base, with the information. If something's round, it can roll away, and a baseball is round. And what new information can we get from that? So starting with our facts and our rules, what can we conclude? Just in general, what new information might I be able to infer from this knowledge base? And so these are primarily the two main approaches to implementing a rule-based system. It's backward chaining and forward chaining. And they're generally in a rule-based AI system are four different components. We have the facts and the rules, which you've already seen an example on the last slide. So we would enter all those into what's called a knowledge base. Then we have, separate from that, an inference engine. So some method of performing inference over our knowledge base of either deriving information or answering questions. We have a working memory, so just a temporary buffer where our rules are loaded into working memory and reasoned over, so where we actually perform the inference. And finally, a user interface. We need some way to enable the user to ask questions to the system. And so the first two components here are an important distinction, which was not initially made in some of the very early attempts at building rule-based systems. But separating the knowledge base from the inference engine enabled these systems to be a little more modular, enable us to use the same method of inference and swap out the knowledge base, or swap out and add rules to our knowledge base while keeping the method of inference the same. So separating those out into two separate components was an important distinction. Now, Peter already mentioned two of the major languages that are used to implement rule-based systems, the one being Lisp and the other being Prolog, which are two of the oldest programming languages that are still in use today. So Lisp is still fairly widely used, and it's the oldest high-level programming language, and Prolog is a little more special purpose than Lisp. It's meant specifically for logic-based programming. And just so you can see an example, using the same knowledge base that I had 2 slides ago, we might encode the rule if something is round, then it can roll away in this way here. So by saying if something X has a shape that's round, then that thing X can roll away. And then we might have a fact that says a baseball is round. And from this, we can reach the conclusion that a baseball can roll away. So we start with our knowledge base by writing all these rules and facts in Prolog, and then we try to answer our question, can a baseball roll away, to resolve our goal, what's called our goal, our query. Now, I want to make a distinction at this point between rule-based systems and neural networks. So where a lot of the focus nowadays is concentrated in implementing these systems is on neural networks and designing neural networks. And this approach is fundamentally different from the rule-based approach. So in a rule-based AI, we encode and reason over symbols. So we might have want to represent an apple, and might represent an apple through a relationship among properties, and build up this tree, this hierarchy of what is an apple. So that's the rule-based approach, which is also sometimes referred to as the symbolic approach, since we're reasoning over symbols. This is in contrast to the neural network approach, sometimes referred to as sub-symbolic, because we don't have symbols explicitly represented in a neural network. We only have numbers and vectors. And these vectors we can interpret and take them to mean symbols, but we don't actually have a symbolic representation in the neural network. So these two approaches to implementing or building an AI are fundamentally different and not necessarily mutually exclusive, which I'll come back to towards the end of this talk. So I want to look back to some of the early attempts at building some of these rule-based systems. So one of the first was called the General Problem Solver. This was built by Herbert Simon and Alan Newell, and it was thought at the time that this would be a universal problem solver, that we would have this inference engine that could solve any problem, when in reality it could only solve very simple problems, like the Towers of Hanoi, which is shown in the image on the right here. In the Towers of Hanoi, we have a goal, which is we are to take all the disks that are stacked up on one rod all the way on the left there, and we have to try to move them to the rod all the way on the right. And we have to do this following a couple simple rules. We can only move one disk at a time, and we can't place a larger disk on top of a smaller disk. So given these rules and the goal state of trying to get all these disks onto the rightmost rod there, a general problem solver could solve this, could come up with the sequence of actions that we need to perform to move the disks from the leftmost rod to the rightmost rod. But it didn't work well for real-world problems, and that's because in the real world, we have a combinatorial explosion. There are just too many states to reason about, too many possibilities that our inference engine would have to accommodate, and so it just doesn't scale. They don't scale to the real world in that way, but it worked well for simple problems like this. Saint was symbolic differentiator and integrator. So it could solve the kinds of problems that you would see on a freshman calculus exam. Actually, they developed this at MIT and then used it on one of the MIT freshman calculus exams, and it got all 52 out of 54 questions right. So it worked reasonably well, but again, using the symbol manipulation, which in calculus, you have rules like the power rule and differentiation by parts and so forth. So using these rules and reasoning over symbols, it could come up with an answer to a differentiation or integration question. The analogy program could reason over shapes. So this program, given the kinds of questions that you would see on an IQ test, the kinds of analogy questions you would see on an IQ test where shape A is to shape B as shape C is to what, it could answer questions like that, again, using this rule-based approach, but it really couldn't do anything outside of that. So it could answer these analogy type questions over shapes, but that's pretty much what it was limited to. And the student program, written a couple years later, could solve mathematical word problems like this that you might also see on an elementary math test. So where we're given some relationship among variables and we have to try to find out what is the value of some unknown variable. Now, this approach to AI, which is typically referred to as good old-fashioned AI. So the rule-based approach is good old-fashioned AI because it was one of the first. It's where a lot of the interest was in building AI when the field was just starting. There was a book written by Minsky and Papert in 1969 about neural networks that basically demonstrated a lot of the fundamental limitations of what are called single-layer perceptrons, which you'll hear more about in the next lecture, but basically established that these neural networks, these very shallow networks, are really limited in what they can do, the types of problems that they can solve. So it's thought that the writing of this book led to a decline of interest in neural networks and the connectionist approach to AI, and a lot of that focus shifted over to the good old-fashioned AI. So a lot of people were at the time now looking at, oh, we can't do this with neural nets. Maybe let's try to do this with a rule-based system. How can we get rule-based AI to solve the types of problems that these simple models can't really tackle? And so at the time, it was thought that this would basically be a problem that would be solved in a couple of years. So Marvin Minsky said, within a generation, the problem of creating artificial intelligence will be substantially solved. Now, shortly after he wrote the book, and coming closer to the time at which some people were starting to realize the limitations of rule-based AI, which I'll talk more about later, but a couple years later, he doubled down and said, well, you know what, from 3 to 8 years, we're going to have a machine that's pretty much equivalent to a human. And so there was a lot of optimism in this approach at the time in being able to solve a lot of the problems that are still considered fairly difficult today, actually. And what happened is, well, it didn't happen. In 1973 and 74, interest in this area really started to die away quite quickly. So this was the result of a combination of a couple different factors. So in 1973, the British Research Council solicited a report, which was the Lighthole report, to basically evaluate the state of AI and the state of what progress has been made. And it came to no one's surprise that really the results up to that point weren't really living up to what had been promised. And so a lot of it sparked what's called the controversy debate, which is what this image is a screenshot of, and led to a lot of funding for AI programs being cut off. All but actually 2 universities in the UK were funding for AI programs was eliminated for all but 2 universities in the UK. And a similar trend followed in the US. So DARPA at that time was a large funding source for AI programs. And we had what was called the Mansfield Amendment, and then DARPA was directed to basically take their funds and only fund direct mission related research and not this basic open-ended research. So this led to the first AI winter, where there was almost a stigma associated with doing AI research in the mid to late 70s. Now, towards the late 70s and early 80s, people started to realize, well, we might not be able to solve intelligence generally in this way, using this rule-based approach, but maybe we can solve some specific problems. Maybe we can build an expert, build a system that is equivalent to an expert for some very specific domain if we were to encode all the knowledge in that domain instead of just all of human knowledge. So maybe we can make an expert instead of just in one specific area, instead of just a general intelligence. And so that's what people focused on in the 80s, is building these expert systems. One good example of this is a system called Enderal, which could reason over how molecules are put together in organic chemistry. So given readings from a mass spectrometer, what compounds might be responsible for that reading. So this required an organic chemist to sit down and write down all the rules, all the information they knew about organic chemistry into a knowledge base in the same format that you saw towards the beginning of the lecture. So in those rules represented in prologue. So write down all the rules I know about organic chemistry, and then we can try to answer questions about what molecules might be responsible for specific mass spectrometer readings we see. There was a system derived from Enderal called Meissen, which tried to determine or identify bacteria that cause severe infections and then make a recommendation as to what antibiotics should be prescribed for that infection, hence the name Meissen. And there was a system called Excon, which is short for Expert Configurer, which would reason about how to build complex computer systems at the time. So at the time when a customer would order a computer system in the early 80s, the components would all have to be selected from different sources, so that the salespeople would have to know which components to order and how to piece these together. Customers would receive the wrong items or wrong information. So this process was automated through Excon, which saved on the order of $25 million a year in automating this process. One of the most prominent projects at the time was Japan's 5th generation computer. So the image on the right there is the parallel interface machine, one of the actual physical machines that was the result of this project. And the name of the project was called the 5th generation computer because it was thought at the time that this was the next step in computing. So we started with vacuum tubes and then moved to transistors and then integrated circuits and then microprocessors. It was thought at the time the next step was to scale out the number of processors, so to build massively parallel machines. And the language of choice for this project was Prolog. So this was going to be a massively parallel inference engine. So it lasted 10 years, and this was a fairly significant effort, almost $500 million. And after 10 years, Japan finally realized that it wasn't really accomplishing the goals that it had set out early on. And so depending on who you ask, the 5th generation project is either a failure or was ahead of its time, because we're seeing the same kind of transition towards many core architectures, towards massive parallelism now as what Shaban was trying to accomplish in the 80s. So in some sense, it was ahead of its time. It was too early in making that step. So Moore's law was in full effect at that time. There was no need really to go towards massive parallelism. Now, expert systems have a couple fundamental limitations, which towards the mid to late 80s, people started to realize. The first is that they don't learn. So I mentioned someone has to sit down, an expert has to sit down and somehow encode all the knowledge that they have about some specific domain into the system. So an organic chemist sits down and encodes all the information they know about organic chemistry into this knowledge base, and then we have Enderal. But it doesn't learn anything new. That knowledge is fixed. It's like a human born with a fixed knowledge, so they don't learn anything. They're also restricted by the size of the knowledge base, meaning if some problem I'm trying to solve doesn't have the necessary information in my knowledge base, then I'm out of luck. So I'm only limited to in the case of Enderal, the 600 or so rules that are in my knowledge base. And because we have this bottleneck, this person that has to hand code all these rules, they're expensive to maintain. So there's a lot of oversight involved in maintaining these systems. One of the biggest limitations, which I'll come back to, is that they lack common sense knowledge. So actually a lot of problems that require intelligence require the knowledge, not the knowledge that you pick up in an encyclopedia or that you get through a course here at NPS, but the knowledge you learn through experience, the common sense knowledge. If I let go of the little clicker here, it's going to fall to the ground. I've learned that just through experiencing physics. And it's this kind of common sense knowledge that expert systems lack, which in some sense is a limitation. So I'll come back to this point. And it's not possible to define some rules. So some rules are actually really hard to define in this rule-based approach. And by example of that, imagine seeing this image and I ask you, what do you see in this image? You tell me a dog with sunglasses and a scarf. Imagine trying to write a rule to solve this problem, which is a perception problem. Well, the image is, in this case, about an 800 by 800 pixel image. We would have to write a rule to account for all the different possibilities, for all the different values of red, green, and blue, if we're looking at each pixel, in which we might have sunglasses and a scarf and a dog. So you can imagine how complex a rule might be to recognize a dog wearing sunglasses and a scarf in an image. So the rule-based approach doesn't scale to the perception problem, where which is actually quite easy for humans, where we just look at something or hear something, we know what it is, we see what it is. So this is considered a difficult task for rule-based AI, and is one of the fundamental differences, again, between the symbolic approach, the rule-based approach, and the sub-symbolic, the neural net approach. Because neural nets, as you'll hear about in the next lecture, are quite good at solving problems like these. So after realizing many of these limitations and understanding that expert systems don't really scale well, they're expensive to maintain, it's difficult to encode common sense knowledge in these systems, this led to the second AI winter, at which point a lot of the companies that were selling tools to build these systems announced layoffs or experienced losses. The Lisp machine market, so the special purpose machines built for reasoning about symbols, for doing this inference, which are referred to as Lisp machines. The Lisp machine market essentially collapsed because people realized, well, I can do the same thing on a general purpose processor like an x86. I can achieve the same performance doing inference on an x86 processor, which is the same kind of architecture that's probably in 90% of the laptops in this room, versus this Lisp machine, which is really optimized only for this one task. And another big factor was the fifth generation project ending. So this reduced pressure, reduced significantly the amount of funding for AI projects in Japan, and reduced pressure as well on funding in the US to try to keep up with the AI arms race that was going on at the time. Now, I want to come back to the common sense problem and try to explain why this is such a difficult problem to solve. So, you've already heard several times over about the Turing test. I want to talk about another test for intelligence called the Winograd Schema Challenge. What the Winograd Schema Challenge says is that if we have two sentences that differ only by an adjective following a pronoun, so we have two sentences that only differ by that one word, where first says the city councilman refused the demonstrators a permit because they feared violence, and the second because they advocated violence. In the Winograd Schema Challenge, we have to try to figure out which object does that pronoun attach to based on how we interpret the sentence. And this is a trivial task for humans. So in the first case, you would say, well, they feared violence. It must be, this sentence must be referring to the city councilman. They were afraid the demonstrators might exhibit violence. And in the second case, they advocated violence. So the permit was rejected because the demonstrators were advocating for a violent approach. Well, this is trivial for us. It's thought to be a task that is a sign of intelligence, but that requires, is a difficult task because it requires that common sense knowledge that you've picked up in either reading news articles, seeing demonstrators yourselves, seeing how government works. So all that common sense knowledge enables you to figure out which object that pronoun attaches to in each sentence. So this is why the common sense knowledge is so common sense knowledge problem is so difficult. Is we would need to encode all that information into a knowledge base somehow in order to correctly do this. Now, if there's one person who deserves an A for effort, it's Doug Lennon, who has been trying to solve this problem for 35 years. So this project is called Psych, and what Psych, the goal of Psych is to solve the common sense knowledge problem. So what Doug Lennon and his company have been doing for 35 years is trying to encode all common sense knowledge that they think might be needed to solve tasks that require intelligence, encode all that common sense knowledge into a knowledge base, and actually doing this process manually, going through and writing down all the rules, like if I drop an object, it'll fall to the ground. Baseball's around, a round thing can roll away. So encoding all that common sense knowledge into a knowledge base, and it's accumulated, it's taken about 1,000 person years so far to do this. And the outcome of whether or not this approach is successful or not, I think is not entirely clear. So actually, Psych only started to commercialize a couple years ago. So Doug Lennon knew at the time that this would be a multi-year or possibly a multi-decade effort. And it was only in 2016 that they just started to commercialize some of the work that they've been doing. So yet to be determined whether or not this approach will be a success or not. They've had some success stories, but so far there's been no breakthrough. So so far it has been the case that encoding, just this brute force approach to encoding common sense knowledge has not led to a general intelligence. So I want to start to conclude by highlighting some of the advantages of a rule-based approach. So I already talked about some of the disadvantages, but there are actually some advantages to building systems in this way, to the rule-based approach. The first is that inference is relatively computationally inexpensive. So computers excel at doing these types of tasks, arithmetic and inference, this high-level reasoning. And this is actually highlights Moravec's paradox, which is that these tasks that seem to require high-level intelligence, like inference and arithmetic. So if I asked you to multiply just two large numbers together, it might take you some time to figure out the answer. These problems that are difficult for humans to perform are relatively trivial for computers to perform. They're computationally inexpensive. We can do them pretty easily. Whereas the perception problems, recognizing what's in that image, the dog with the sunglasses and the scarf, taking an image and figuring out what's in the image, that's a trivial task for humans. We see something, we know what it is. We hear something, we know who it is or what it is. Whereas it's a relatively difficult task to get a machine to do that. Another big advantage of rule-based systems is that they're explainable. So we start out with a bunch of facts and rules and then arrive at some conclusion, and we can trace exactly the steps that we took to get there. So we know exactly why some conclusion is true or false, or why through forward chaining we came to some goal. This is not so the case for a neural network. So this is actually an advantage of the rule-based approach over neural networks. There's been some progress in recent years, and there's a lot of interest in trying to make neural networks explainable, but generally it's a difficult task, whereas rule-based systems, we can explain how we arrived at some goal. And really into that, they're well suited for problems that require symbol manipulation and high-level reasoning. So the board games that Peter mentioned, playing chess and Go and checkers, but other types of problems that require symbolic reasoning, like trying to navigate through the London tubes, trying to look at a map and figure out how do you get from point A to point B, or looking at a family tree and asking what does it mean to be a great aunt. So looking at all these relationships, these rules between members in this family tree, and just answering the question, what does it mean to be a great aunt? What does that relationship look like? And so that's actually the direction that some recent work is going in, is looking at an integration between the symbolic approach, these rule-based systems, and the sub-symbolic approach, the neural nets. And in my opinion, this is the future, is a promising direction to pursue in building intelligent systems. So this image is from a paper from DeepMind. This architecture shows what's called the differentiable neural computer, which is really just a gigantic neural net. It's a big neural net, but the way this neural net is designed, the architecture of the network is such that we have a almost something that looks like a Turing machine. We have a mechanism with capable of reading and writing, and then a separate place to read and write to memory. So this buffer that we can use to store and manipulate variables. And in this way, this network can reason over symbols. It can work with symbols and answer the kinds of questions that I was just talking about, and manipulate pointers to objects in memory. So I think this is an interesting area of research and something worth looking at. So with that, I'll conclude the talk and open the floor to questions.